Thank you so much for checking out the Weaviate podcast. Today is going to be another super exciting episode. We have Yaoshiang Ho from Masterful AI. Masterful AI, from my first impression of it, looks like this super interesting model training and deployment, computer vision software. And I'm super excited to just dive into the details and get right into it. So Yaoshiang, thank you so much for coming on the podcast. And can you tell us about Masterful AI?
Yeah, absolutely. Glad to be here. Thanks for having me. So you asked about what we are, but let me just set the stage a little bit so you kind of understand the problem. So obviously we know kind of deep learning became a big thing in the mid 2010s. AlexNet, kind of groundbreaking performance. Google acquires the company behind AlexNet, gets Jeffrey Hinton as part of that deal, and a lot of use cases have been cracked with it, including then deep learning also applying to NLP, not just CV. So then kind of looking at the tooling a little bit, like back in the day, you had to access GPU through shaders. So thank God, at least there's like CUDA now, and then TensorFlow and PyTorch built on top of it, and cloud providers offering hardware really easily. But all these platforms are still really hard to use. Like you have to be a deep learning expert, and as you know, it takes years to become a deep learning expert. So if I would describe the problem today, it's sort of like there's no equivalent of a MySQL database or Node.js, much less a Stripe or Shopify. There just aren't these like high level services and platforms to solve all your problems. Yeah, there's TensorFlow, but it's basically like having to program all of those libraries I just mentioned in C++ yourself just to get an application going. So let me answer your question, really directly. Masterful is a platform to build computer vision models, and it simultaneously has a very simple interface, and internally it has the most advanced algorithms. So kind of think of like when you go to AWS and fire up a terabyte of S3 storage. It's so simple for you, like 3-4 clicks, but behind the scenes, there's all this machinery going on. There's all this, hardware being procured, and connections being made. The advanced algorithms inside are what makes it like really ready to deliver production ready models. And I would contrast that with some other AutoML platforms that are out there in computer vision. So it's got a meta learning engine. It's not an off-the-shelf one. It's one that we built just for our engine. And what that does is it takes away a lot of the hyperparameter tuning that a developer has to do. And that's what delivers on that promise that you pass in the data and you get them all. It's not you pass in the data, run 500 experiments, track them all, and just sit and act like a human grid search algorithm for like 5 weeks, which is kind of how you do it today. It also delivers the best regularization policy. Regularization means basically it means getting the most information or training the most accurate model from your labeled training data. And then on top of that, it has a semi-supervised learning engine, which means your model will get even more accurate data, get even more accurate from the unlabeled data that you pass in. So that means images with no labels. That technology is available today. I think you saw our technical report, so you saw some of the algorithms that we've kind of adapted, including like Noisy Student, Barlow's Twins, and SimCLR. So that's what the platform is today, and the problem it's trying to solve for developers.
So with our Weaviate audience, I think the SimCLR and Barlow Twins implementations are just super relevant to what we're doing, because that's where we get these embedding models that produce vector representations that optimize for semantic similarity. But breaking down the things you said, we have, and then also the meta learner, the hyperparameter sweeping, and reminiscent of things like weights and biases and determined AI and all that kind of user interface for your model training stuff. But so I'd love to kind of break these things down and go into them one by one. And I know the Weaviate listeners probably want to go into Barlow Twin SimClear first, but can we actually start with Noisy Student? Because I think you have some really interesting perspectives on the Noisy Student implementation in Masterful.
Yeah, so Noisy Student is kind of conceptually drawn from a well-known idea of knowledge distillation, which is like one model generates soft labels from unlabeled data, and then there's a noise function, and then a student model gets trained as well. And that's kind of like the basic theory. And I think to contextualize it, where Noisy Student is arguably advanced and different from SimCLR and Barlow's Twins, sort of the unsupervised training techniques, is Noisy Student, I think, was one of the first to prove that it could work at very high cardinality data, whereas some of the other techniques were more optimized for lower cardinality data sets. So, for example, a lot of times, like if you look at the original SimCLR paper, they'll use like 1% of the ImageNet labels. And so you're using a much smaller cardinality, like on the order of 10,000 labeled examples, whereas Noisy Student was kind of trying to prove that they could do it at very large cardinality. So they did full ImageNet, 1.3 million images, and then used Google's proprietary JFT 300 dataset with 300 million unlabeled images to then further show that you can actually improve on ImageNet supervised training without necessarily adding additional model architecture size, although that helps as well. But I think one of the things I want to point out, since your audience probably understands some unsupervised pre-training techniques like SimCR a little bit better, there is a very strong similarity between these, and it's not often thought about. But in both cases, you are training two models kind of at the same time. You are
Mm-hmm.
noising the inputs between those two pairs of models, and you are trying to get them to match up with each other. So although noisy student often is thought of as a teacher and a student, ultimately you are trying to get two models to match, just like Barlow's, just like SimCLR. And then the loss function in noisy student is obviously kind of a weighted cross entropy, whereas in SimCLR it's contrastive, and Barlow's has their exotic loss, which kind of adds its own kind of variance, covariance, and sorry, I forget the third part of Barlow's loss function. But ultimately, you are trying to get two parallel paths to take the same image, noise them, and then see if they can ultimately match. So they're not as different as you might think, because when you kind of lay them out side by side.
Yes. Yeah, I love that perspective of the similarity between teacher-student knowledge distillation and then Siamese copies of the same network as we're trying to learn representations. And then maybe just a quick, I do think most listeners probably are aware of this general paradigm of contrastive learning, but the idea is that you have a Siamese copy of the network, say this is your BERT model, and this is also that same BERT model, and they run it, and then they get the vector embedding, and they'll be, you want them to align positive pairs and make it dissimilar to negative pairs. So that's kind of the background behind that idea. So just to sort of lay the foundation a little bit in case we dove right into it a little too quickly.
Sorry about that.
Well, that was my fault with the way that I set that up. But let me, so noisy student, for one, this idea of high cardinality, such an interesting insight. I'd never made that connection before, I guess I wasn't aware of the history of it, that they were trying to show that knowledge distillation can work for, say, in a 1,000 label set. Could you take me a little bit through that before we move on?
Yeah, less about the number of labels, but more about the number of examples. So, as we know in computer vision, the classic data set, 1.3 million examples in ImageNet. So again, just to repeat, like with SimCLR, often they'll take 1% of the labels and treat the other 99% of the images as your unlabeled set. And so the point there is they say, hey, off of just 10,000 labeled images, we can get really, really good accuracy. But we have to use 1.2 million unlabeled, or draw from that pool of 1.2 million unlabeled images. Whereas with Noisy Student, they said we're going to use all 1.3 million labels from ImageNet, and then we're going to take 300 million more images to use as the unlabeled data set, and prove that we can still improve the accuracy of the model. There's a talk that a guy named Gadaris gave, and I'll send you the link to it so you can append it in the show notes, where he kind of contextualizes just kind of where these kind of ideas were kind of fitting in with each other, and why they kind of were solving slightly different problems. I remember when I was reading SimCLR, I'm like, why does SimCLR use this really tiny data set, and why does Noisy Student use the full one? And there is a little bit of a history, and they were trying to solve like slightly different nuances of the problem of SSL.
Wow, yeah. Thank you for that. I think that's a really interesting angle to it that I hadn't thought about. Kind of the direction I was thinking we were going to go in is talking about the noising used in Noisy Student, and how we
Mm-hmm.
have the augmentation. And as I was going through the Masterful documentation, I saw this phrase, augmentation clustering. I read that, and
Yeah.
I need to know what that is. What's the idea
Yeah,
behind
yeah. Well, let
that?
me tell you, just give you a very brief history here. So, I mean, within Noisy Student, there's three types of noise that happen. There's just classic data augmentation, which by itself is extremely powerful and sufficient to make it work. And they add two other forms of regularization that I'm sure everyone's aware of. I mean, one is dropout, which is classic, and maybe another one that maybe is not as used as much as stochastic depth. But the point is that to get these techniques to work, you have to have the right regularization technique. You cannot just throw in, I'll just do a couple image blurs and a zoom and a darkening, and I'm sure that'll work. Like these techniques are very fragile. So in a sense, when you talk about noisy student training, people get excited more by the student because it's kind of architecture based. But you could argue the noise is at least as important to the idea of noisy student training. And what we found in the lineage of, let's just take data augmentation, is that there's a very strong sense of overfitting to ImageNet. And ImageNet images all have a similarity in the sense that they're all taken by humans holding a camera. Whereas a lot of other applications don't have these attributes. Geospatial in manufacturing, sometimes the cameras are very fixed. Sometimes they're very precise. Sometimes you don't. A satellite doesn't go up and down, or I guess some do, but a lot of satellites stay in geostationary orbit, or at least at the same altitude. Like they have the same resolution no matter what. If you've got a camera pointing at a manufacturing line, like that is it. That camera is not going to move around. So that's some of the explanation, I think, of why a lot of the classic ideas of how to build a good regularization policy, in my opinion, are just kind of overfit to ImageNet. So kind of the lineage that kind of we study, and we mentioned this, is kind of the AutoAugment and then RandAug. And AutoAugment is a very, very deep search. The problem with the depth of that search is it's 15,000 runs in their paper, full training runs to figure out the correct policy. So that's obviously, just intractable for any like normal developer. And then RandAug, which I think is still considered state of the art because I think SimCLR used it, tried to reduce that search space by clustering. They didn't use this term, but if you kind of think about it, that's what they did. And the search space reduces down to about on the order of 100, searching the number of transforms and the magnitude of those transforms. But the insight that we had is that the way that they clustered those transform magnitudes was just on a scale of 0 through 30. And they would basically test all the transforms at level 1, all at level 2, all at level 3, etc., and then all at level 30. So, they didn't specify the search algorithm specifically, but their point was in the paper, the search space is small enough to simply grid search. So presumably that's the algorithm they use. 100x is still way too long for any practical person. I mean, if you're renting, AWS machine for $24 an hour, like, good luck telling your boss I'm going to need 100x more time, instead of $2,000, I'm going to need $200,000. Like, forget that. That's not going to happen. So what our insight was, and it's kind of based on a very, very simplified version of an idea from GANs, which is Frechette inception distance, is the distance of something really can give you insights into how much you're perturbing the image. So maybe darkening or brightening an image by one click affects it very little on the darkness transform, but maybe on the rotation transform, it's extremely destructive. And so that means that instead of just saying, I'm going to search click 1 of darkness and click 1 of rotation, what I really should be doing is searching click 1 of rotation and click 50 of darkness, because they're more equivalent when you look at the distance that the image generates. So how do we calculate that distance? I mean, you can have your choice, right? You can do very exotic distances. You can do L2 of the feature maps. Another thing you could do is just calculate the difference in the scalar losses when you rotate an image in forward prop versus darken. So that's how we run forward prop to try to understand how much all these transforms affect the model, perturb the model from some idea of a distance from the unperturbed images, the non-noised images. Once you have that, then you can very quickly cluster like 5 big clusters and then grid search 5 clusters or 3 clusters instead of grid searching 100 clusters. So that's a little bit of a nutshell. And I apologize, we haven't quite published that algorithm in detail, but that's the kind of heart of it, is instead of clustering just based on some heuristic of magnitude, we actually impute these magnitudes based on how much it perturbs a model's performance on specific data.
Wow, that is super. That is so interesting, and I do want to kind of just get a couple of terms. So just because you're so knowledgeable, and I really just want to dive in, but I also want to sort of lay the groundwork for people listening. So again, in noisy student, the teacher labels the data for the student network to learn from. We're going to augment that data for the student to learn from. So we have data augmentations like rotation, blurring, cropping, flipping, making it more blue than usual. Like there's a massive set of image data augmentations that are label preserving. So then came along the algorithm RandAugment. RandAugment has 2 hyperparameters, N and M. N is how many to apply in sequence, and then m is the magnitude to, because each one has an associated magnitude with, say, rotation. You're either rotating at 60 degrees, negative 60 degrees, or say 30 degrees, right? So the clustering Yaoshiang is describing is n and m. They define a cluster in this space of the massive configuration of the n and the m that you could have. So then for Shea, inception distance was this thing used in GANs that's like, GANs are a generative model before diffusion models kind of stole the show, where it's like real fake loss. And you say, how do I say that these generated images are quality images? So what you do is you have the vector space of the generated images, and then you have the vector distance of these generated images to your original images, and so that's that kind of foundation. So now I think where we are is we're looking at the vector distance between augmented images and the original images to
That's
define
exactly right.
clusters of augmented images. And so this is super relevant for so noisy student, of course. So you're saying which augmentations should we apply to the image for the teacher to label for the student, but also for our general framework of training contrastive learning models that produce like the vector embedding models that go into Weaviate, is we have to have this algorithm where we start with an image or any data point. If we'll keep it to images because
Yeah.
that's like what most of the label preserving data augmentation research has been done on. So we start with an image, and then we're going to transform it into the positive image and then align those vector embeddings. That's the training objective. Okay, so I hope that was like a decent little like kind of primer to it. So now let's dive a little more into this idea of, okay, so we're augmenting images, and then we have semantic clusters that come from the augmentations. So is that, I mean, do augmentations really like throw off the semantic representations so much? I know that there's like an issue with robustness with these models where, say,
Hmm.
you take your test set, and if you rotate all the images, suddenly you might go from like 90% to like 60%.
Yeah.
So
Yeah.
in your experiments, these augmentations, they create like very different clusters.
I'm not sure how to answer that. I mean, the purpose of these clusters was to cluster all of our transforms by the distance or by how much it perturbed the model. So I think what's interesting is maybe I'll answer it this way. If you look at a lot of research when they're classifying ImageNet, they're just going to use a human prior and do a mirror, for example. But if they're classifying MNIST or SVHN, they're like, oh, I shouldn't do that because numbers shouldn't be horizontally mirrored. And indeed, what we find is if you rotate a numeral by 180 degrees, or you mirror it, models are just going to get really confused by them. And so you see that reflected in the amount of distance that comes out when you measure the intermediate feature maps or the final value. So that immediately tells you that's a fairly destructive transformations, and it usually gets excluded very quickly by the search algorithm. So I'm not sure if that's exactly what you're asking, but yes, we do find that this approach kind of automatically figures out these ideas. I think another thing that maybe happens in geospatial a little bit is because the objects are often very small. I mean, the order of single digit, double digit pixels, as opposed to ImageNet. This is my hypothesis. I haven't done the study to prove this, but if you rotated the image of me by 5 degrees, you'd say, oh, that's still me, no problem. But when you take something that's like 3 pixels by 8 pixels and you rotate it, you're starting to get aliasing issues, right? The old computer graphics idea. You're losing resolution. You're adding blur to it, and so what we've also found is a lot of times in geospatial images, these mild rotations end up being very destructive. In a sense, the more mild, the worse it is, because the more aliasing you induce. A 45-degree rotation is much better than a 2-degree rotation. I'm not gonna prove that. I don't have a paper to justify it. We haven't done all the studies, but I'm just kind of giving you a flavor of some of the things that we've kind of observed as we try to explain why our algorithm has discovered, made certain decisions about the right policy for, in this case, data augmentation, and applies to regularization as a whole, of course.
It's kind of reminding me of this idea of like, so out of distribution detection,
Mm-hmm.
and so using the vector representations of images to determine that so we're up in a satellite, and we've got, I think you look at like crops or something. I'm not an
Hmm.
expert on this kind of thing, but and it's rotated such that you really have you've corrupted the label. It's no longer label preserving. So from the vector
Hmm.
representations of the images before and after augmentation, does that give us enough signal to uh, do out of distribution detection? Would I don't know if maybe I shouldn't have said out of distribution. I should have said just
Hmm.
like label corrupting. But
Yeah,
generally,
yeah,
this idea that you've lost the information and you can tell
yeah.
that purely from the vector space, and thus you have this heuristic to say, let's actually not have the teacher label that for the student and noisy student. Is that how it comes? Or when we're training SimClear models, let's not make these positives because that augmentation is no longer a positive.
Yeah, we don't use this technique to take things out of distribution and adjust the label as much as we just treat it as a non-label preserving, not sufficiently label preserving transform, and we don't use it. Typically in these regularization policies, you kind of have one policy, and so you run it, and the goal is that one policy will sufficiently perturb the data. So it's not identical, but it's still within distribution. So it's still, you know. Uh, feels like natural data to the model. If you and I eyeball it, usually it looks like relatively normal. But again, it's that's just trying to explain what's kind of happening inside. What's happening inside is it's easy to define kind of mathematically, but it's hard for me to truly tell you why it's working. These are just sort of my interpretations of why I've seen these policies come out very differently for very different types of data sets. I think the broader point is that you have to be adaptive to the data set. And it kind of goes back to the point I was saying that a lot of research is overfed to ImageNet. And ImageNet, people think it's hard. There are a lot of things that make it really easy, actually. It's a balanced data set, for one thing. There's very high entropy in this data set. Um, it's all handheld cameras taking it. So there's all these attributes about it that I think researchers probably kind of like overfit to. And when you try to apply any of these techniques out to production data sets in the real world, you just see how it just doesn't work nearly as well as it does on ImageNet or Cipher 10 or something like that.
Hmm. Could could we maybe stay? I kind of want to explore one more idea in the space of
Yeah.
using the vector representations and how they change. And I'd like to kind of dive into this idea of active learning, and I think it's maybe relevant to
Hmm.
the Masterful model training suite. And
Yeah.
active learning is basically this idea where let's forget randomly sampling the next batch. Let's try to intentionally find the next batch of data that would be the best one to train on.
Yeah.
And I've seen papers like focusing on the biggest losers, where you say,
Hmm.
take you had your batch of 64, this one had a huge loss, and so maybe you do like a vector search with something like Weaviate to go get more like that, because that's like clearly like a weak spot in our data
Right.
space. Do you
Right.
have any thoughts on that kind of idea?
Yeah, absolutely. So it's on our product backlog to, let me step back a little bit because a lot of our unlabeled data comes from video feeds. The problem some of our customers have is, well, video, if you treat it as a sequence of frames of images, you've got a lot of it. You get to millions and billions of frames really quickly. So the question becomes, I can't train on all of that. So my naive algorithm, my null case would just be randomly sample it or uniformly sample it. I can't sample all of it. But like, can't we do a little bit better? And so indeed, we have done some research internally on using exactly that, active learning ideas to say, well, what can I pick off from these, millions and millions of frames? Can I find like the 1% that's going to help my model learn the most? And I think one of the first algorithms, like a lot of us go towards is, great, we'll just pick the one the model's wrong on. That's got to be the one to fix. And sometimes that's right, but sometimes that
Mhm.
doesn't help because sometimes what ends up happening is you force your model to get really good at these really rare examples at the expense that it forgets all the simple examples. So like you may have solved that 1% really hard problem, but the 99 simple ones, you just degraded that performance by 50% because your model wasted all this energy. So it's like it's not as easy as as I think we think when we first start this problem. And um, uh, so some of our internal research in this area is probably less oriented towards the vectors, although we have ideas on that as well. But a little bit more kind of going back towards the GAN idea or the generative adversarial network is to say, can I train, can I again, typically is thought of as generating synthetic images. And the training is that there's a generator that generates the image and a discriminator that tries to decide if that's a real image or a fake image. And they fight each other in a so-called mini-max competition. So you train one and you train the other. Sort of the analogy people give is a counterfeiter and a policeman. So you train the counterfeiter by having the policeman tell you, is this a counterfeit or not? And then you freeze the counterfeiter and you have the policeman now try to train itself to get better by telling it the reality of whether this is a counterfeit or not. So these two kind of compete with each other to get better. And so without giving too much away, we have a similar idea that the generator is not really generating synthetic images, but just in this case has full knowledge of whether it is a labeled image or an unlabeled image. And the discriminator tries to figure that out. And if we can get to the point where we can trick the discriminator into thinking that an unlabeled data image is labeled, then maybe it's going to think, maybe that gives us an algorithm to pick the most useful unlabeled images, the ones that don't look like labeled images. In other words, the ones that are not going to, the ones that are actually going to, sorry, let me start over. If we can train a discriminator using this GAN thinking, but not a true kind of GAN in the classic formulation, then we may be able to use that discriminator to pick out the most valuable unlabeled images that can teach the model something without being so hard that it's going to destroy what the models learn, but not being so easy that you're just wasting your time, backpropping on really simple images. So that's sort of some of the heart of how we've been kind of thinking about it. So apologies, it didn't go into the vector space, but our thinking there is a little more inspired by sort of the discriminator of a GAN.
Yeah, I think I had something I was going to ask you, and then I think I gained a better understanding of this idea. And so purely from an unlabeled image, the discriminator would be able to tell if it's been labeled because you also have a classifier that's been trained on a labeled set. Like, how does it connect the information?
Yeah, the discriminator could have information about would have information about the vectors that come out of a trained model, either the final prediction or the intermediate feature map. So those would be the vectors or the embeddings. And based on that, its job is to predict, is this data point labeled or not? And you kind of use that to figure out these are the ones that are too easy, so don't send it to them. These are the ones that are too hard, and here's the ones that are right on the bubble where there's still some learning value that's not going to trigger forgetting of some kind. Yeah, again, a little more inspired by the kind of GAN discriminator concept than necessarily sort of vector distances. Although we have other ideas on using vector distances in other active learning type ideas where similar problem. Just can I be more intelligently pick the data to spend my money to label as opposed to just randomly sampling data points I'm seeing from inference or using human judgment to find visually go through the data and look for clusters. Like, is there some way to try to automate that?
Yeah, the way that I originally described active learning is I remember a paper called Mind Your Outliers. That is setting visual question answering data sets and that exact idea of which one was the biggest loss. And they find that you cannot, it's impossible to answer that, and that's why it is. So yeah, being a little more clever about that. So semi-supervised learning. And as I went through the Masterful documentation, that jumped out to me as looking like one of the big focuses of Masterful is on the semi. Obviously, we talked about noisy student, where in addition to having the image that it's not just like you have the labeled data set and you take the image, apply noise to it, teacher labels it, student learns it. It's also like you have unlabeled data as a part of this kind of thing. And that's the idea of semi-supervised learning. You have labeled data, big unlabeled data set. And I'm sorry if these names, have you heard of the ADA match, the kind of that kind of approach where I think the key thing is they have a loss function at the label layer and then also in an intermediate representation of the teacher.
Got it.
Kind of. So I guess kind of the question is what's the landscape of semi-supervised learning look like? What are kind of some of the cutting edge ideas?
Yeah. So you're describing, some of them, which is kind of stepping back. When you take the pair of models and you ask them to kind of match up, you get to pick whatever kind of layer to try to match up. And I'm not up to date on A to match, but it sounds like you're trying to get intermediate layers to match up as well as the final layer. You can argue that, in noisy student, you're getting the final layer to match up, which is a post softmax. So it looks like labels, but the fact that this label is almost not as important as the fact that they just had to pick some feature map, some output of a convolution and ReLU. And in a lot of other models like Barlow's, then they stack on a whole bunch of other layers, which they end up throwing away, and then you just use an intermediate layer. So almost think of like, you got ResNet 50 and then you force it to do, and just throw away the final layer. So you have just ResNet 45, and you just find that the intermediate layer is more generalizable in some way, whereas the final layers get too task specific towards the pretextual task that you're using. Pretextual means you've created a task for these models that is on the surface not actually solving your problem, but through solving that pretextual problem, you end up solving the problem you actually care about, which is to learn better representations, which will get you a more kind of accurate model. So I think one of the most interesting things is, I think when you look at semi-supervised learning, although, as I mentioned, noisy student and then the unsupervised pre-training techniques like Barlow's and SimCLR look very different. They actually have a lot of similarities ultimately. But setting that similarity aside and looking just at the idea of pre-training, this is in the first paragraph of the SimCLR paper. They talked about contrastive as one basic idea, but the other one being generative. And so generative, they actually cite Goodfellow's GAN paper. So could you train a GAN and then use the representation in a GAN to act as a technique for building an unsupervised feature extractor? And the conclusion broadly was, no, those representations waste too much energy trying to get pixel perfect images, and so they aren't generally very good. But kind of the latest right now is transformers and feature reconstruction kind of taking over, where you just take an image and then you literally add white noise to the pixels of an image, and you ask the GAN to kind of reconstruct that. And that apparently has turned out to be a very interesting and powerful technique for the model to learn representations inside and become a very good feature extractor. And I think it goes back to some older research that did not beat state of the art, but it is, I think, very well known at this point. One was to colorize images. So if you have a color image, turn it to black and white, and then train your model. It's not exactly an autoencoder. It's kind of an autoencoder at that point to colorize the image. And then Godaris, I think his first name is Spiros. I don't want to butcher it. I think around 2017 or 2018, he did a classic paper. It was just sort of a proof of concept, just rotating the image 90 degrees, 180 degrees, and 270 degrees. And then your pretextual task in that case was to predict the amount of rotation of the image. And they just found that these models did learn an interesting representation inside. It may not have been better than supervised training on ImageNet, but it did learn something, and that was just really cool at the time. So then the next question was, when does it get better than supervised? And that's where SimCLR kind of was such a breakthrough in that for 1% of labels, it actually does train better than a supervised technique. So sorry, you asked a more direct question and I wandered a little bit, but it's just such an exciting area. And
Yeah.
it just always frustrated me that you need labels because images have information. So it's not a feature that you need a label. That's a bug. I mean, there's nothing that holds, there should be nothing that holds a model back from learning from images, without labels. So this whole field is just, super exciting.
Yeah, and you're so knowledgeable about it that it inspires so many different ideas that I listen to, and there's so many questions there's so many directions we could go in. But so the question I'd want to follow on with is, so this idea where it can so I kind of want to pivot into say CycleGANs and the image to image translation thing, and to kind of build up this idea, the idea that you classify the rotation angle. So you rotate it, you say that's a 45-degree rotated airplane.
Yeah.
The CycleGAN image to image translation idea would be like you rotate the airplane and then it's like unrotate it.
Let's see that. Yeah.
so I've been thinking about this idea about like, could this help with distribution shift, where the distribution shift happens kind of, and it can sort of map it back to the original
Yeah,
thing.
yeah,
It's,
absolutely,
does that idea
absolutely.
make sense?
Yeah, I mean, CycleGANs were, I mean, the cycle part was just a consistency to try to prove that, if you can go from horse to zebra back to horse very effectively, then the cycle was kind of completed. And so it was a way to kind of enforce the goal. But the real task was not the cycle part, but, a technique called, image to image translation, which says like, if I have um, a horse in a pose, can I then generate a zebra in that pose, and can I then generate a dog in that pose? And so I'd suggest people look at the series of papers that Xun Huang, I believe, studied at Cornell under Belangi, generated. And his first idea was neural style transfer, which we all know just by looking at the layers, but then adding the same ideas but with adversarial losses. So the concept from GANs then allowed these more like really even more powerful techniques. Um, We've researched that area quite a bit, particularly for domain adaptation, as you described. We looked at one scenario where there are two major satellite providers, and although visually you look at the images, they look the same. If you train a classifier just on one, it won't do very well on the other. It'll be like 2/3 of the performance. So could you use some of these techniques to do an unsupervised image-to-image translation? Um, and what we found was, and it may go back to that first paragraph of the SimCLR paper, which is when you, well, maybe it doesn't, I'm not sure about that, but it seems like a lot of energy is put into visually appealing translations, but it kind of doesn't really fool the model that you're trying to train. So we were not able to successfully perform domain adaptation using these techniques. And I think if I had to hypothesize, I think at least in part, again, image to images are often very large objects, very well framed. And in the geospatial applications that we were applying, you've got much smaller objects. And so it was a much more difficult challenge. If you have a picture of a horse that's taking up 75% of the pixels and you translate that into a dog, I'm suspecting that'll probably be useful and more believable. But this is probably, I think, the more I'll go out on a limb. I don't think this is backed up by research, but I think my observation of just of generative adversarial of adversarially trained models in general is that they seem to work better for these very large, well-cropped images as opposed to lots of fine-grained images. So in the
Mhm.
applications we've tried it, we were not able to get success. I do think there are some startups in the space of combining 3D generated graphics, but then using GANs for more textures, which presume maybe that's where we're a little bit stronger. So you can imagine having a 3D game engine generate some street level imagery, and then use a GAN to kind of texturize it into rainy or nighttime scenes. Maybe that adds more diversity to the data. Um, I can imagine something like that working. Haven't done the research myself.
Yeah, I've always been excited about this idea that we can just use kind of data augmentation, maybe even like the way that CycleGAN enables a more flexible interface to cover a
Hmm.
bigger distribution of our data. And it
Yeah.
seems to me like deep learning can always fit to the training set almost. So it's like if you just blow up the training set with these priors about semantic preservation, sort of, that you can just do anything sort of with it, has always been
Yeah.
something I've been thinking about. I wanted to kind of dive. You
Well,
referenced
let me
this
just pause you
application.
real there and just mention that what it seems like these adversarially trained approaches, the distribution actually gets narrower, not more
Mm,
diverse. So,
mm,
I mean, if you just fire up StyleGAN and you look at the faces that come out of it, you're like, oh my God, these images look fantastic. They look so realistic.
mhm.
But then,
Yeah.
like, if you just, even the paper they admit themselves, part of the reason they look so good is they're sampling kind of the very narrow parts of the
Mhm.
distribution. When you push that latent, the embedding, push it to really wide, it just gets really kind of like broken. So there's actually a shortage of diversity, not too much diversity, but not enough within, and that's why it looks so good. It's maybe, and again, I'm going to go out on a limb. I don't know if this is true, but maybe that's why they look so good. Is they get really good at delivering the 100,000 faces, really effectively, but they can't really represent the full, diversity of 6 billion different faces. I think the GitHub for that paper that Xun Huang's a co-author on, FUNIT, Few Shot Unsupervised Image Translations. It's called FUNIT. Has an image of a dog rotating and all these other breeds of dogs rotating the same way. And you're like, wow, they've really transferred that over. But look closely, all the noses are the same size. So that's just a little trick. You just stare at it long enough, you start noticing these little tricks. Like, oh, did it really do a full translation to all species, breeds of dogs, or is it just believable to me and you that these 10 dogs look similar, but it actually doesn't really represent anything close to the full diversity of dog breeds, much less dog poses, much less dog poses in different environments. So maybe that's one thing I'll just go out on a limb and say. How about I call that future work / hypothesis rather than conclusion or trend?
Yeah, well, that inspires me thinking about like I recently dove into a paper called Augmax where they flip it to its friendly adversarial training, and they also do this like t-SNE space clustering where they show you
Mm-hmm.
that certain generative techniques, they exactly as you described, they just make it super dense on the but
Yeah,
it's still like
yeah. Nice. I hadn't read about that, but obviously, I'm familiar with t-SNEs and love them. Actually, our logo is actually inspired by a t-SNE. Like when we were designing the logo, we said it should be blobby like a t-SNE. So that's exactly why our logo is what it is.
it, oh yeah, I see some cool art where it's like sorry, I'm gesturing like a t-shirt. I haven't seen this on a t-shirt yet, but I've seen like the data set used to train Hugging Face's Bloom model. I've seen that put into an embedding space, and it's like colored by languages, these kind of t-SNE.
Yeah. There's
Yeah,
a
that's so.
the TensorFlow embedding has an open source tool. You can just cluster MNIST, and it'll all the dots will fly around. You can use other clustering techniques. I think UMAP and but yeah, the idea that these things are meant to be blobby. This is the real world. This is not a tabular world. Like if we were a tabular company, we'd have a grid, right? Like a good tabular world where everything's
Yeah.
neat and organized. But no, this is messy. This is deep learning. This is the real world.
Yeah, and well, yeah. So I guess it's like so we certainly could continue this conversation for a while. I think there's quite a few ideas in this whole thing, but I do want to kind of step out a little bit for the sake of keeping our podcast a little dense and maybe kind of asking about like how you see the Weaviate vector search technology playing with Masterful and it kind of coming back into like the tools and the software that exists.
Yeah, absolutely. So, I mean, just stepping back to, our goal is to provide more high-level tools for developers so they can access all the power of deep learning without, spending 2 years becoming, deep learning experts and reading all the papers you've read, right? Like what person building a backend app was going to read all the papers on relational theory and relational algebra and relational calculus? Like, you don't have to do that anymore, right? You learn enough SQL to do what you need to do, and you got all this power that's sitting behind the surface that you don't need to know about anymore. I mean, that is the vision we're trying to get to here. So we currently support classification, object detection, and semantic segmentation. And obviously, there's a whole bunch more computer vision tasks that we want to support. And there's something unique about similarity search, whether you're applying it for computer vision or for text, which is in classification and the other tasks I mentioned, once you have a trained model, you're ready to go to inference. Put it up in TensorFlow serving or Onyx runtime. Put it on a Kubernetes cluster, or you can use easier packages like Google Vertex endpoints. You're ready to inference. You're ready to run inference. Integrate with your app. In similarity search, you are not done once the model's trained, because now you've generated all these embeddings and you've got a million of them. Well, now I've got to search over all of them. So to deliver a complete product to our users, obviously we need to partner with a company like Weaviate, because you got to put those embeddings into the database to then allow users to do that reverse lookup, indexing down through those embeddings to then rediscover like which faces is this, or what building or what room is this embedding represent. So our initial, I think, thought on working together just as a proof of concept would just be to use a classifier that's trained using our techniques of supervised and semi-supervised techniques, taking an intermediate embedding and just seeing is that sort of a good enough MVP embedding, just to kind of prove the point that we can build an end-to-end product that involves training and the vector search database. And so once we can prove that, then it gives us more confidence that when we do kind of do a full-on hardcore similarity search support, that we'll already have all the integration set up so we can deliver a complete solution for our customers. So again, they don't have to understand hierarchical small navigable world. They don't have to, understand RandDog. They don't have to understand SimCLR. They can just say, hey, I got these two tools that'll solve all that for me. Put in the training data, out comes a trained model, run the embedding, put the embeddings in your database, and now I've got a way to look up any image by running inference, get the embedding, look it up in the database, and I can figure out what's the nearest, image or person or thing that this image represents. So I'm excited to pursue that, and we've already started some of our proof of concept work on this.
Yeah, that's super interesting. I love, I mean, perfectly said. The combination between the model training, the end to end, and then having the database where you store the representations that have been learned, and then the way that these HNSW structures, you don't want to do dot product with a million images.
Oh my God.
Yeah. So the way they play together is so interesting, and I think that's also like kind of the interpretability of it. Like when you have a object detection inference, you can be like, it looks like this. I've seen this kind of thing before. Sort of. Do you like that kind of interpretability play of it? And sorry, actually, I think this is a good chance to kind of. We talk about retrieve then read pipelines all the time in natural language processing, because in natural language processing, it's so intuitive. You have data sets like Squad where you say, what is the atomic number of oxygen? So naturally, if you retrieve the context of Wikipedia going oxygen, the atomic number is 8, and then you just can classify it there. So with NLP, it makes so much sense. But can I ask about this retrieve then read for computer vision tasks like classification, detection, and segmentation, to just start there?
Yeah, well, I would frame that as I currently would think of similarity search as a separate computer vision task to support. In addition to our binary classification, multi-label classification, single label classification, object detection, semantic segmentation. Other computer vision tasks we want to support over time would be key point detection, instance segmentation, pose estimation, object tracking. But what's a little bit unique about this is we've built in some unsupervised pre-training techniques, which as I think, as you know, are even superior methods to generate embeddings. But it's also superior to a user because they don't have to label their data to get the similarity search necessarily. The labels will help. It's yet another data point. I'm not sure if I've answered your question, but I would just frame it as another computer vision task for us to support. And then, like I said, as a proof of concept, we thought, could we just take a classifier trained using traditional techniques and use that embedding as a similarity search, just as a proof of concept to get our products to work together with the supported tasks that we have today. And like I said, that already seems to be a positive.
Yeah, super cool. And yeah, I think with like self-supervised similarity learning is so sophisticated in computer vision with, again, SimClear and Barlow twins. The data augmentation interface is so strong that you get this search thing works extremely well without labels. And I think that's just incredibly interesting. Can I ask, like, broadly, what drew your interest to computer vision? If you could kind of tell the story of...
Yeah. It goes back a long way. So it goes back to just being a gamer in high school. And, some people like me get excited about, can I render my own computer graphics at some point? And so there's that, I went and started my computer science program in undergrad at Berkeley. I put down computer graphics as a specialty for it. And once you render something, then you want to know what you rendered. And I remember hacking Z buffers just to try to figure out, basically you would call it segmentation today if you could access the Z buffer, frustrums and all that stuff. And I had a professor, John Forsyth, who wrote an image classifier for horses, and that basically ended my interest in computer graphics and computer vision in the 90s, because it was just so heuristics based. It was just all these handcrafted ideas. If we just throw this and this and this and wait, all these little handcrafted rules, then maybe we can figure out what a horse is. And I said, that is just so not elegant. And I ended up going to databases, ironically enough, having a chat with a guy from a database company, because databases are applied algorithms. B plus trees are just wide red black trees. And, it was just such an elegant space, and indexes, no question, my favorite part. And so it was a really enjoyable for me to learn about HNSWs and just seeing an index applied to a graph instead of a vector or a heap. It's been nice. Anyways, so I was out of computer vision, from the 90s until about 5 years ago. So my co-founder Sam Wookie, our CTO, he stayed in computer vision. He's founded a startup. He ended up selling to the NFL to track, player movements on the field, pre-deep learning. And when deep learning came out, I didn't know anything about it, but he was following all this stuff. He's like, "Oh my God, deep learning can crack all the computer vision problems that like I thought were uncrackable at the time." So he left Microsoft and joined Google just so he could kind of join the mecca of deep learning and kind of learn the secrets. So uh, Sam said to me, "All this stuff is working. Take the Andrew Coursera course on ML to get up to speed. Take the Andrew deep learning specialization." And I hadn't programmed in 15 years, and I did. And first of all, I realized I enjoyed programming. But second, again, and then secondly, I was just amazed by the power of deep learning. Like, holy cow! From all those heuristics from that John Forsyth paper. And I'm not denigrating his paper. It's just that was the state of the art at the time, but it just wasn't for me. But there's just an elegance to just having machines train themselves. And so I was hooked. So that's sort of my return, my first and second love affair with with deep learning and computer vision.
That's the magic of deep learning. The whole input output.
It's amazing. It's absolutely amazing.
Yeah.
It's amazing.
Yeah, I had the story of Sam and the NFL thing. I the first computer vision project I dove into is I had full basketball games and I was trying to extract like made baskets. And I think once, like, kind of coming back to your point about ImageNet and being object centric, and I got started studying like CFAR 10, the much easier version of ImageNet. And yeah, once you get into like a real problem, you really appreciate these things like class imbalance or just the challenge of labeling data and why these semi-supervised, like, once you get a real project, you'll really appreciate the semi-supervised learning thing just because of the cost of labeling the data and all that cool stuff. So one other question I really want to ask you about is your experience at Masterful AI. Can you tell me about the inception of Masterful and all that kind of stuff?
Absolutely. Well, I mean, the beginning of this story is just exactly where my last story, trailed off, which is, Sam got me super excited about deep learning. He was at the Mecca, at Google, but he started telling me some of the ugly truth about deep learning, which is huge models, huge compute budgets, huge labeling budgets. And Sam instinctively was just like, "This is cool, but like, how do we make this work for, just maybe companies with two deep learning engineers, or maybe just a general, software engineer, like a lot of our friends who, don't want to spend 2 years learning all this stuff." And that was the basic instinct that he had, and he thought the technology was there to achieve that, which is all the stuff in our platform. And then on the flip side, the technology may have been there and it may have been his instinct, but I wanted to see if there was really a market demand for it. So I linked up with another friend of mine who I respect a lot, Tom Reichert, who's now my third co-founder. He had been a venture capitalist, or was then still a venture capitalist, and had been one for about 10 years. And so I really trusted his insight in kind of what the market was. And in particular, he wasn't one of those guys who was investing in social media networks. He was investing in deep tech, and so he invested in a lot of AI companies. And he said, "Yeah, I've seen lots of startups trying to commercialize deep learning, and it's incredibly hard to get the models going." So kind of between my inspiration in the space from Sam and his kind of idea that the technology was ready to go, and then Tom saying, "Yeah, the demand is there," we said, well, if both of those things are there, then it's the right time for us to kind of build this startup to kind of bridge that gap. And so that's the birth of Masterful. So I've got two just absolutely amazing co-founders in Tom and Sam, and we embarked on this journey.
Can I ask about, without sort of saying like, could you describe the competition in the space? Could I ask about sort of the category that you think that Masterful falls into and some adjacent categories?
Yeah, absolutely. The most narrow and closest adjacent to us would be the AutoML providers. And we live up to the same promise as AutoML: feed in data and get back a trained model. Where we've been a little reluctant to brand ourselves there is we philosophically are not in the same place as most of the existing AutoML providers. They are very neural architecture oriented, whereas our hypothesis fundamentally is more data centric. We think it's a lot less interesting to try to fine tune the perfect model size, and it's a lot more interesting to understand, how to get the most out of those architectures. So in our command line interface, for example, you can select the right architecture. We think you should pick the architecture based on your inference latency, throughput, cost requirements, which you can predict just from the architecture. So if you're on an edge device, you may need a certain device. If you have want maximum accuracy, then pick efficient at B7. You're going to get like 99.9% of all the improvements that you can from architecture just by doing that. The interesting thing is, how do you manipulate the data through regularization? How do you add unlabeled data?
Mm.
So I would say that they are broadly our competition, but we have a very different philosophy. And not to plug my product, but we've put out the blog report showing how we beat like Google Vertex AutoML on a whole series of data sets, because I think we take a more holistic approach and a more data centric approach to the problem. Kind of expanding the ring a little bit, thinking about less as just sort of data in and model out. Think of this as dollars in and more accuracy out. You might say that we also kind of maybe you might imagine we kind of bump up against like active learning a little bit. Again, this idea of can I be more efficient with my labeling spend? But the good news is we don't really compete in that space as much as these are complementary techniques. People can easily have both. That kind of contextualizes kind of where we fit in the space, and kind of what other platforms somebody might be, comparing us to, depending on what profile they're in.
Awesome. Well, Yaoshiang, thank you so much for this. I'm so grateful for you taking your time to do this, and I'm so lucky to have like such a information heavy podcast in our Weaviate podcast collections. It's really amazing. So thank you so much.
I've super enjoyed it. I didn't realize we were going to go like this technical, but I'm glad we did, because it's just so inspirational, and sometimes it's hard to describe to my parents like why this stuff is just so exciting. But I mean, the breakthroughs are just it's it's a perfect moment where there's a ton of commercial opportunity, so there's a lot of money to fund this research, and there truly is like just groundbreaking stuff coming out. I mean, it's deep learning is going to be way more important than the internet, in my humble opinion, because it touches real world things. It touches where people really are out there, driving and thinking, and looking at agriculture and manufacturing. It's just I'm super excited by the space.
Yeah, awesome.